Hello viewers, my name is Dr. Ajay, Associate Professor with the Department of ECE from the Institute of Aeronautical Engineering College, Hyderabad. Today we are going to discuss about the problems on directivity and radiated power. Today we are going to discuss about the problems on directivity and the radiated power. So these problems belong to the first unit of the course Antennas, Waves and Propagation. So the course name is Antennas, Waves and Propagation. So we are going to discuss about the problems related to the module 1 of the antennas. Let us start our session today. Let us start with the first problem based upon the directivity. The first problem is the radiation efficiency of certain antenna is 95%. The maximum radiation intensity is 0.5 watts per steradian. Calculate the directivity of an antenna if P input is given as 0.4 watts and P the rad is equal to 0.3 watts. So we need the radiation efficiency of an antenna is given as 95%. And the radiation intensity, the symbol of radiation intensity is denoted as pi. The radiation efficiency is denoted by the symbol eta. So we need to calculate the directivity, which is denoted by the symbol D. So we know that the directivity is given by the radiation intensity, the maximum radiation intensity. The maximum radiation intensity of an antenna is known as the directivity of an antenna. Or we can also call it as pi max by pi AV. So directivity, the definition of directivity is the maximum radiation intensity to the average radiation intensity. We define it as the directivity. Also, the efficiency of an antenna is denoted by power radiated to the total input power. So, how much amount of power is radiated to the total input power? We call it as antenna efficiency. So here, the given parameter, we need to write down the given parameters here. So what are given in the data given in the problem? The radiation efficiency is given as efficiency eta is equal to 95%. So eta is equal to 95% means is equal to 95 divided by 100. This is equal to 0.95. We can write. So the maximum radiation intensity, it is given as pi max. It is given as 0.5 watts per steradian. Here the units of radiation intensity can be measured as watts per steradian. So first we need to calculate the directivity for this input. We need to calculate the directivity for the given input. What is the input given here? The power input is given as 0.4 watts here. So we know that the formula efficiency is equal to P radiated divided by Pi. So P radiated is equal to Pi. So what is the radiated power here? So we need to calculate the power radiated. Why? Because the power radiated in the problem, the data is not given, but efficiency is given. The efficiency is given as 0.95 and Pi it is given by 0.4 watts here. So from this we can write as efficiency is equal to 0.95. This is equal to P rad, radiated power. P rad means radiated power divided by input power. This is equal to 0.4. So if you simplify this, you will get P rad is equal to 0.4 into 0.95. So 0.4 into 0.95. This is equal to, you will get approximately 0.38 watts. So approximately you will get P rad is equal to 0.38 watts here. So efficiency is given as 95% here. So from the basic formula of the efficiency is given by radiated power by input power, which is given as P rad by 0.4. So P rad is equal to 0.4 into 0.95. This is equal to 0.38 watts here. 0.38 watts here. So based upon the power radiated and the power input, we can calculate the directivity. So here, if we simplify the directivity here, we know that directivity is equal to pi max by pi AV here. So the maximum radiation intensity to the average radiation intensity, we call it as directivity. So we know that pi average, it depends upon the power radiation. So here the power pi AV, it is a function of power radiation. So pi AV is equal to W by 4 pi. Pi AV is equal to W by 4 pi. Already we know that pi AV is equal to W by 4 pi here. And if you substitute this W by 4 pi here, you will get pi max by W by 4 pi here. If you substitute here 4 pi is in the denominator, you can take this 4 pi into the numerator, 4 pi into pi max by W. So this W is nothing but power radiated. So from this equation you will get 4 pi into the maximum radiation intensity. It is given as 0.5 watts per steradian. 0.5 watts per steradian. So you can substitute here 0.5 divided by power radiated, we got as 0.38 here. So power radiated we got as 0.38 here. So if you simplify this, you will get 16.53. So this is the directivity for the input power is equal to 0.4 watts. So this is the A bit here. So directivity is equal to 16.53 it is for the given input power. Now the next problem is P rad is equal to 0.3 watts. So already it is given in the problem as P rad. So we need not calculate again P rad separately. But for the first case, for the A bit, P rad is not given. That is, the rated power is not given. Hence we have calculated this P rad value. This P rad value is calculated for A. But for B, it is given directly as P rad. So we can directly calculate the value of D. So for B, you can take D is equal to pi max. So 4 pi into pi max. This is equal to 4 pi into pi max. What is the pi max value? It is 0.5 by power radiated is given as 0.3 watt. So power radiated it is given as 0.3 watts here. So 4 pi into 0.5 by 0.3, if you simplify here, this is equal to 4 into 3.14 into 0.5 by 0.3 here. So here if you calculate here, 4 3s are 12 and 12 by 2 means approximately 6 you will get, and you will get 6 by 3 means 3 by 10 into 10. So approximately 60 by 3 means you will get 20 point something you will get here. So here you will get D is equal to 20.95 here for the B bit. So this is how to calculate the directivity of an antenna for a given data. So here the radiation efficiency is nothing but the radiated power to the input power. So also the directivity of an antenna is given by in terms of maximum radiation intensity and the average radiated power. So directivity, it is the ratio of maximum radiation intensity to the average radiation intensity. So if you substitute these in these values, you will get the value of directivity as directivity is calculated as P input is equal to 0.4 and P rad is equal to 0.3 watts here. So you can see here in the figure, the efficiency is given as P rad is equal to P rad by Pi, and efficiency we have substituted here 0.95 is equal to P rad by 0.4, and also here if we say cross multiply here, you will get P rad is equal to 0.38 watts. So from this expression we are going to calculate D value, pi max into 4 pi by P rad. This is the A bit here. So similarly for B bit, again you take the formula for directivity, that is the directivity is equal to pi max into 4 pi by P rad. So D is equal to pi max into 4 pi by P rad. So that is equal to 0.5 into 4 into pi by 0.3. So this is equal to 20.95. So you can also, this is just a decimal value. You can also express the directivity in terms of dB just by converting this into dB. So D is equal to 10 log D base 10. So by this formula, you can also calculate, express the D in terms of dB here. So 10 log D base 10. So if we simplify this 20.95 here, you will get the value of D in dB here. So let us come to the second problem here. Antenna operating at a wavelength of 2.5 meters has a directivity of 90. So determine the maximum effective aperture. Determine the maximum effective aperture here. So aperture, so effective aperture, it is nothing but it is given by AE is equal to, the maximum effective aperture is given by lambda square by 4 pi into directivity. So this is the relationship between the directivity and the effective aperture. Effective aperture. So the effective aperture is defined as the Poynting vector, the power incident on the antenna to the Poynting vector of the incident wave. We call it as the effective aperture. So the effective aperture and the physical aperture both are different. So how much whichever the portion, this is the antenna here, if the radiation is falling in this area, so we call it as effective aperture. So this is the actual aperture, and this is the physical aperture. So suppose if we say an antenna, take an antenna here. If we take an antenna here, if this is an antenna, so its length is 1 meter here. So if the radiation is falling, this is known as actual length, or we can also call it as the physical length of the antenna. If the radiation is falling only on this portion, then this portion we call it as the effective aperture. So where the power absorption takes place on an antenna, we call it as an effective aperture. So there is a relationship between the directivity and the effective aperture of an antenna. So which can be here we can write it as AEM is equal to lambda square by 4 pi into D. Here the wavelength is given as lambda is equal to 2.5 meters, and the data directivity is given as 90. So simply it is given in a decimal point. So we are having a formula, D is equal to 4 pi by lambda square into AE, or AE is equal to lambda square by 4 pi into D. So here lambda is equal to nothing but 2.5 square by 4 into 3.14 into D here. What is D value? 90. So if you simplify this value, you will get 2.5 square into 90 by 4 into 3.14. You will get 44.76 meters square. You will get 44.76 meter square. So this is a simple problem based upon the effective aperture of an antenna. So first, if we want to solve this problem, we need to know the relationship between the directivity and the effective aperture. So it is D is equal to 4 pi by lambda square into AEM. Next, let us see about discuss about the problem 3. A microwave link is to be designed such that the transmitting and the receiving antennas are separated by a distance of 30 miles. By a distance of 30 miles here. So the directive gains of both the antennas are equal to be 45 dB. Assuming both the antennas to be lossless and matched at 3 GHz, find what power is transmitted to have a received power of 1 milliwatt. So we need to calculate from the given data the power transmitted. So a microwave link is to be established here. So here there is a microwave link to be established here. There is a transmitting antenna. Here there is a receiving antenna. This is the transmitting antenna and this is the receiving antenna. The distance is separated by 30 miles. The distance is separated by 30 miles here. So we know that we need to convert this into meters here. Why? Because 1 mile is equal to 1609.35 meters here. So 1 mile is equal to 1609.35 meters here. And always it is given as in the data, the directive gains, it is given as both the antennas to be equal to 45 dB here. So GT, let us assume the transmitting gain of the antenna as GT. Let us assume the receiving gain of an antenna as GR. And GT, it is given as is equal to GR, it is given as 45 dB here. So GT is equal to GR is equal to 45 dB, it is given in the data here. And again, it is given, that is the frequency. The frequency of the transmitting end is given as 3 gigahertz. It is given as 3 gigahertz here. So as per the given data, we know that GT is equal to GR is equal to 45 dB. It is given in the data here. This is in the dB value. We need to convert this into the decimal value. So always it is very simple for us. It is convenient to have mathematical simplification to express the dB in decimal value. So we need to convert this dB into decimal value. So we know that 10 log GT is equal to 45 dB base 10 here. So we can write this GT as log GT is equal to 45 by 10 here. And here you will get, if you convert this value, you will get GT is equal to 31.622 into 10 power 3. Here log GT is equal to, here log GT. So log GT is equal to, you will get 4.5. Log GT base 10. So log N base A is equal to B. Therefore N is equal to A power B. So we are having the logarithmic formula here. So log N base A is equal to B. So we know that N is equal to A power B. So if you simplify this, you will get the value of GT as 31.622 into 10 power 3. Similarly, if you simplify for GR also, you will get the same value. You will get 31.622 into 10 power 3. So this, we got the decimal value of GT. And again, we need to find out the frequency. It is given as 3 gigahertz. We got the frequency as 3 gigahertz. Hence, from this equation, we know that C is equal to F lambda and lambda is equal to C by F. So C is equal to 3 into 10 power 8 by, the frequency is given as 3 into 10 power 9 here. So if you simplify this as 1 by 10, you will get this is equal to 0.1 meters. So this is the lambda value. And similarly, we need to calculate the R value. The distance between the transmitting antenna and the receiving antenna is given as 30 miles. So 30 into 1609.35. So 1 mile is equal to 1609.35 miles. So meters. So this equal to, you will get 48,280.5 meters. So this is the data we need to find out first to find out the power transmitted. So after finding out all these values, so from Fritz's transmission formula, we know that there is a relationship between the power transmitted and the power received. So GT by GR is equal to, there is a relationship between the power received and power transmitted. WR by WT is equal to GT GR by 4 pi R by lambda whole square. WR by WT is equal to GT GR by 4 pi R by lambda whole square. So from this equation, we need to calculate the WT value. So the received power is given as WR is equal to 1 milliwatt here. So what is WR? 1 into 10 power minus 3. WT we need to find out here. What is GT here? 31.62 into 10 power 3. This is again the whole square here. Why? Because GT and GR are equal, by 4 pi into, the value of R is 48,280.5 by lambda 0.1 whole square. So we need to simplify this, you will get the value of WT here. So by means of the calculator, if you simplify the mathematical expression, So that is 1 into 10 power minus 3 by Wt is equal to 31.623 into 10 power 3 whole square whole divided by 4 pi into 48.280.5 by 0.1 whole square. So from this equation, you will get the value of Wt. So Wt, if you simplify this, you will get 36 watts here. Approximately, you will get 36 watts here. So this is the given data here. So Gt is equal to Gr is equal to, we got 3 gigahertz, and Wr is given as 1 milliwatt, and lambda is equal to 3 into 10 power 8 by 3 into 10 power 9, you will get 0.1. And we need to convert the dB value into decimal value here. So 31.622 into 10 power 3 here. So if you substitute all the data here, given data, so you will get here, this implies Wr means you will get 1 milliwatt, 1 into 10 power minus 3 divided by Wt. So this is equal to 31 point, what is the value? 31.622 into 10 power 3 into 31.622 into 10 power 3 whole divided by 4 pi into 48,000 point. So we will get 48 to 80.5, 48 to 80.5 by lambda, it is 0.1 whole square. So all, if you substitute here and simplify, you will get the power transmitted, that is equal to 36.8115 watt here. So 36.8115 watt here. So these are the problems, and the references for these are antennas and waves propagation, UA Bakshi, and you can also refer the Balanis textbook or John D. Cross here. We are having the John D. Cross also. So you can refer the problems for KD Prasad, antennas and wave propagation, India publications. So the first edition 2001 here. So today we have discussed about the problems on directivity, effective aperture, and the fixed transmission formula. Based upon the fixed transmission formula, we are going to calculate the amount of power transmitted or the amount of power received. Let us close our session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.